And this one is 2.16. Here we have a sloop, which is nothing but a small ship, which I have shown you right here, with a single mast. And what is the mast? This support structure that you see here, this is the mast here. And on this mast you can see in this figure that there are these cables that are going down in this manner, and this figure is drawn for you here. Now the diameter of the cables is given 1 centimeter diameter, and these cables are going through a spreader which is right here in the middle. These masts are made with wood, and the cross-section area for that is given as 150 centimeters square. For the cable, that is this part right here, the stiffness is given, which is 250 kilonewton per centimeter for a length of 0.5 meter. So in the process of mounting this whole thing, first we brought it up, and then we use these turnbuckles. What are these turnbuckles? These are these small devices that are attached to these cables, and the role of these devices is to adjust the tension or the length of these cables there. And for these turnbuckles, every time you make 10 turns, it's going to move by 1 centimeter, and we are moving it by 15 turns, so basically we are moving it by 1.5 centimeters. What we need to figure out here is the compressive force in the mast, which is the wooden part here. So we need to figure out the compressive force there. So first let's analyze the forces and see if we can solve for the system. So let's put some names here. This one is A, this is B, this is C, and this one is D right here, and this one is E. So if you look at your member AD here, on this AD there will be these tensions coming from the cable in this manner, okay, and there will be this compressive force. So let's call this FAD. Now for the tension here, we will put 2 times T here, because there are 2 cables on both sides of this member AD. Now this angle right here, let's take this as theta from this figure. So you can write an equation for Y force balance here, which is your FAD force needs to be 4T cos theta, and from the x direction you are going to get that 2T x component will cancel out from there. Now let's look at the other part of the structure, which is this body right here. Now you can see that there are these cables going this way here, going down, and this is attached with these AD and D members also. So if I draw FAD, which is going up here, FAD will come down on this one, and similarly if I assume FDE, this member also to be compressive, then it's going to apply a force that goes vertically up on this one. Now again this angle right here is going to be 90 minus theta. So now if I write the Y force balance for this, we already have this FAD equals to 4T cos theta. Now these are again 2T here, 2T here, and 2T there. These are the forces coming from the cable. You can notice that FAD, this 2T and this 2T, they will be following this equation and they will cancel each other. So effectively in the Y direction from this, we are going to get FDE equals to 4T. So now we have got one equation here and we have got the second equation there. And how many unknowns we have in this? We have FAD, FDE and T. So there are 3 unknowns and we have only 2 equations. So we need to have a third equation, which will be your geometrical compatibility equation or the deformation relationship. Now for the deformation, let's look at this structure. Originally this structure is like this. This is A, this is D, and this one is E here. So this member AD will be slightly compressed in the beginning. So only AD is compressing right now. So this A moves to A dash, this is D, and this one is E. Now after this, if we consider the compression that's happening in member DE also, so this moves to new place, D dash, E, and this is A double dash. So this is where we reach finally. So now if you mark these deformations here, this deformation right here is your delta AD, and this deformation that we notice here is your delta DE. Now if you want to draw the cable here, your cable is going to be connected this way and this way, this way and this way. So the final length of this cable, these points are B here and C here, B, C and B, C. So this one, let's call this as B dash, and let's call this as C itself. So if you notice, the final length of this cable is going to be A double dash B dash, that's coming from here, plus B dash C, right? Now since B dash C and D dash E is going to be same, so we can say that this is equals to plus D dash E. Now this A double dash B dash, this length right here is going to be same as this, because this is only considering the deformation happening in AD member, right? So I can write this as A dash B plus D dash E. So how do we calculate A dash B here? So let's look at this height. Originally this was given as 5 meters, this was 2 meters, and this is 10 meters. So A dash B is nothing but the slanted length here, which is square root of 2 square plus 5 minus delta AD square, because the length of AD has reduced slightly. And your D dash E right here is going to be 10 meters, which was the original length, minus delta DE. So in calculating the final length of this cable here, only delta AD is playing role, and the final length of this member here, the delta DE is playing role. So I can write down the final length now. Final length L dash equals to square root of 2 square plus 5 minus delta AD whole square plus 10 meters minus delta DE. Now the original length for the cable L is basically this one right here, which is 2 square plus 5 square, and the vertical height BC, which is 10 meters. If you think in terms of deformation, your delta cable is equals to L dash minus L. Now from where this deformation is originating, this deformation is coming from two factors. First factor is the tension that is present in the cable, and second factor is the turnbuckles that are tightening your cable. So because of tension, your extension is going to be a positive, and because of these turnbuckles, because we are reducing the length there, we are going to have this delta TB. Now this number we already know, because there are 15 turns there, and each turn is causing 1 centimeter divided by 10 there. So overall this is going to give us 1.5 centimeters. Now in this side we can write down the relationship that we have written: 2 square plus 5 minus delta AD whole square plus 10 meters minus delta DE, and this is L here, which is minus square root 29 minus 10. And this relationship, this is the geometrical compatibility, or the third equation that we are looking for. This third equation here, this has a square root there, so of course we can solve it using any numerical method, but let's see if we can find a approximate solution. Okay, so if I expand this inside, so this is 4 plus 25 plus delta AD square minus 10 delta AD, and this 10 and 10 cancels out here, so minus delta DE minus square root 29 equals to delta T minus 1.5 centimeters. Now here, this assuming that these deltas are going to be much smaller, I can ignore this term from here, and if I take square root 29 common from this term, we can write this as 1 minus 10 delta AD divided by square root 29 to the power half, and all the terms can be written as it is, equals to delta T minus 1.5 centimeters. So at this step, assuming that this number is much smaller than 1, we can use that formula which says 1 plus x to the power n is equals to 1 plus nx when x is much smaller than 1, so that we can get square root of 29, and 1 minus half times 10, that will give you 5 delta AD square root of 29 minus delta DE minus square root 29 equals to delta T minus 1.5 centimeter. So now this one, if I multiply the square root, this cancels out with this. So effectively this gives us minus 5 delta AD minus delta DE equals to delta T minus 1.5 centimeters. Now these relationships for delta AD can be written in terms of FAD times length of AD divided by elastic modulus and area for AD. Similarly, delta DE can be written FDE times LDE divided by EDE divided by ADE. Now for both of these, your forces are expressed in terms of T. So if you recall, your FAD is 40 cos theta and FDE is 40. So both of these relationship, this becomes 40 cos theta delta AD times LAD, which is 5 meters, divided by elastic modulus for wood. So approximately we can take a value of 10 GPa here, and the area for this is 150 centimeter square, so we can write 150 centimeter square there. Similarly for delta DE, this force is 40, length for this is 10 meters, E is 10 gigapascals, and area again is 150 centimeter square. So now this is done, this one is done. Now delta T here, which is your deformation in the cable because of tension. So T times the overall length of the cable, which is the slanted length, which is square root of 29, plus vertical length, which is 10 meters. So this one is in meters, divided by EA. Now how do we get this value of EA? Now the K value for this cable is known, and using Hooke's law, we know that this is EA over L. So this is given as 250 kilonewtons per centimeter, and that is for a length of 0.5 meters, which is equals to 50 centimeters. So if I multiply this on this side, I get a value of EA, which is 12500 kilonewtons. So I can use that value right here. So now you can see that all the terms in this equation we have expressed in terms of T. So T is the only value that is unknown in this equation right here. So if I substitute everything there and solve for the value of, let T comes out as 7.08 kilonewtons, and because your FAD and FDE are related to T using these two relationships, these values are FAD equals to 26.32 and FDE equals to 28.34 kilonewtons.